welcome to another video. It's that time of the year again. It's Advent of Code and we're gonna have so much fun. I'm gonna try to get all the way to 25, but we'll see how many days I will actually handle. And usually when we have this kind of intro, I have some sponsor shots here. But this year, the sponsors that were reaching out was mostly AI companies that didn't really meet the actual seal of approval for me. They weren't really having a product that they could go to market with yet. So this year, as the creator economy is a little bit strange, I would much rather think that you should give some of your appreciation to an other creator. So I will put my donation link in the description, and I don't really care if you give me money. You can if you want, but I want you to pick out some creator that you watch regularly, that you really like what they do, and then give them a small donation saying, hey, I really appreciate what you do. So that is my call out for this year. Let's get into some Advent of Code. Good morning. Day 7. Laboratories. Thank you, the cephalopods, for the help and exit the trash. Thank the cephalopods for the help and exit the trash compactor. Finding yourself in the familiar halls of the North Pole Research Wing. Based on the large sign that says Teleporter Hub, they seem to be researching teleportation. You can't help but try it for yourself and step into the large yellow teleporter pad. Suddenly you find yourself in an unfamiliar room. The room has no doors. The only way out is the teleporter. Unfortunately, the teleporter seems to be leaking magic smoke. Since this is a teleporter lab, there are a lot of spare parts, manuals, and diagnostic equipment lying around. After connecting one of the diagnostic tools, it helpfully displays error code OHNO, which apparently means that there is an issue with one of the tachyon manifolds. You quickly locate the diagram of the tachyon manifolds, your puzzle input. A tachyon beam enters the manifold at a location marked S. The tachyon beams always move downwards. Tachyon beams pass freely through empty space. However, if a tachyon beam encounters a splitter, the beam is stopped, and instead a tachyon beam continues from the immediate left of the immediate right of the splitter. Let's see, in this example, incoming beam enters downward from S until it reaches the first splitter. At this point, the original beam stops and 2 new beams are emitted from the splitter. And those beams continue downwards until they reach more splitters. And at this point, 2 splitters create only 3 tachyon beams. These both are bumping tachyons from the same place between them. This process continues until all of the tachyon beams reach the splitter exit manifold. To repair the teleporter, you first need to understand the beam splitting properties of the tachyon manifold. In this example, a tachyon beam is split a total of 21 times. How many? Analyze the manifold diagram. How many times will the beam be split? So, 21 times the beam is split. Okay. So we pretty much want to look for this case where we have one above and a splitter, and there we will have 1 split. Here we will have 2, 3, So this is, let's see, 6, 9, 13. This is 16. And then we have another 6 times. Is that 21? Let's see here. 3, 3, 3. That's 9. 3, 3, 3, 9. 12. 16. 22. Right? If you only count the splitters. Or is it one of these splitters that doesn't split? Where it doesn't touch in the top. Yeah, this one doesn't split. So that's why it's 21. I see. Well. It shouldn't be that impossible, I think. I think the easiest thing to do here is to start off by creating a map again. So we do an int array, map, new int array. And here we want to have lines size. And this is height. And then we want to have width equal to lines get 0 length. And we do width times height. String line. And we do line split like that. And we do a start X. If this equals S, then we have a starting position. So the starting position, should that be -1, for instance? And in case of a splitter. We set the 2. Otherwise, we hope it's 0. We can do an erase fill map with 0. This should be the case. It should be 0 values, but let's do it explicit like that. So I think we could do an start x as well and set to idx here. Because we know that that is the first line, it will be y0. So that's fine. Should the start position just be a 1? That could be the case. So for int y 0, y smaller than height, y plus plus, and then we do the same for x. Like that. Yes. And we start at y1. And then we don't care about the starting position, and we want to split. So when we come to this position, we want to check the position above us. So map y minus 1 times width plus x. If that is equal to a 1, so we know that the thing above us is a 1. Then we want to check this current position, and if that is equal to 2, we want to split. And then we want to check here I think we could so if map this map minus 1 is equal to 0, then that is equal to 1. And I think we could count the split here. And we do the same for +1. Else, so we have a splitter. We don't have a splitter, and the one before us is then the current value should be equal to 1. I think. And if we print that out, what do we get? With then we get 21. So I've already counted all the values there. And if we just run false here, we got 1533. We put that in. We get a gold star. I get a gold star. You get a gold star. Everybody gets a gold star. So let's go to part 2. With your analysis of the manifold complete, you begin fixing the teleporter. However, as you open the side of the teleporter, you replace the broken manifold, and you are surprised to discover that it isn't a classical tanical manifold, it's a quantum Tarkon manifold. With a quantum Tarkon manifold, only a single Tarkon particle is sent through the manifold. A Tarkon particle takes both left and right path for each splitter encountered. Since this is impossible, the manual recommends the many worlds interpretation of the quantum Tarkon splitting. Each time a particle reaches a splitter, it's actually a time itself which splits. In one timeline, the particle went left, and in the other timeline, the particle went right. To fix the manifold, you really need to know the number of timelines active after a single particle completes all of its possible journeys through the manifold. In this example, there are many timelines. For instance, there is one timeline where the particle went left, or there's the other timeline where the particle altered through left and right each splitter. Or there's the timeline where the particle ends up at the same point in the alternate timeline, but takes a totally different path there. In this example, the total particle ends up to be 40 in the different timelines. Apply the many worlds interpretation of the quantum Tarkon splitting in your manifold diagram. In total, how many timelines would a single Tarkon particle end up on? So this is one of the more mathy things. It's not really a computer science thing, but maybe we can figure it out anyway. So we want to check the cases where it could end up. So let's do day 7b. That. And just for fun, just put in the split there. And what do we get? I thought that we should get more than... Oh yeah, we have not run the same file. There we get 32. That's not right. This has to do with permutations, and you need to figure out how many permutations you have for each line. So for instance, if we have this one, we come down here, we have one permutation, and then we have two permutations here, we have 3, 3, 4, 3, and 5. And we are back. Let's just try to make this recursive instead. That could be fun. So if we store this one, for instance, like that. And then we return permute splitter, and we take a map, and we take 0 and the x value, like that. If y equal to and of course we need to add width and height here as well. Like that. And if y is equal to height, return 1. So we are at a particular position, so map y times width plus xx, and what we want to check is the value beneath us, which should be +1. If that is a splitter, then we run splitter map y plus 1 okay, call that x instead, x minus 1 with height also want to check if map minus 1 is equal to no, maybe we don't, because that is a case as well. So what will this give us? That will give us 26 or 47. What? Do we get 47 again? Zero? Yeah, we need the else statement. Else we just run this down x. That goes to 40. Okay. So recursively going down actually got us the right result. Let's try and see if we can get the right result with the non-test case as well. It's going to be a lot of splits. Going to be a deep hierarchy. With a lot of different branches. And we are back, and as you see, it hasn't completed yet, and I think I'm gonna leave it here. So this is a way that you can either solve it the way I've done now. This is probably one of the solutions to this problem. The other way you can do it is calculate how many splits you have in each iteration, and do some math after you Google the actual algorithm, and then you will get the result as well. This is something that you never will have to apply in any work situation at all, and it's frankly not that interesting to me. So I'm gonna leave it here, and this is gonna be the video for today. If you have a better solution, or if you have Googled the algorithm, leave a comment in the comment section down below. If you haven't subscribed yet, please do that. If you like this video, give it a like, share it with your friends and colleagues, and I really want to see you in the next video.